Okay, guys, can you guys hear me? Okay, guys, can you guys hear me? All right, let's give it maybe one more minute while we're receiving more students. Okay, today is like the first lecture for our new session. We might have some new students, they have some technical issues getting into our classroom. So let's have it one more minute while we're waiting for the new students. All right, it's 7:01, so let's get started. Okay, guys, welcome to our lecture. You're currently in a lecture which is our knowledge-based lecture, session 2. In this lecture, we're going to be focused on the counting and probabilities. For some students who actually joined us from like the bootcamp lectures, the Euclid or AMC bootcamp lectures, so a quick introduction between these two different series. The bootcamp lecture is kind of like a more concentrated lecture. You have 10 lectures to cover everything for the Euclid, for the AMC. While our knowledge-based lecture is more like in-depth, more detailed lectures. We're going to use a one session, 10 lectures talking about one topic. So that being said, in the knowledge-based lectures, we're going to go for more details, more into the ground, give you guys the rationale, the background, and different type of problems, questions, so on and so forth. While in the bootcamp lectures, we're going to do something fairly fast, just give you something flash, everything to you right away. So it's kind of like a two perspectives when we are trying to do some study, right? Some foundation, some basic concepts, or have something fairly quick. All right. So in this session, like I mentioned, this is our session 2, counting and probabilities, which is extremely important concept for the math competition. And I do understand a lot of students, they have some challenge, they have some difficulties, try to understand the concepts and also try to utilize the concepts, the different rules, try to solve some problems. So this is actually basically where we come from. We like to use this basically 10 lectures together, give you guys an overall understanding how to do such problems. All right, so before we jump to our lecture number 1, I'd like to give you guys a quick overview, something like a content, what will be covered in our 10 lectures. Okay, so in our lecture number 1, we're going to focus on some basics, counting and probability basics. We're going to introduce some very, very important rules, something just like, enumeration, right? Casework, multiplication principle, the sum rule. So these are something very understandable, very basic, but will be considered as the foundation for the entire counting and probability. And then moving forward, we're going to spend some time talking about the permutation and the combination. So these two concepts are considered to be a twin brother, right? You keep seeing this from any kind of problems. We're going to use the permutation, I'm going to use combination, or maybe the combination between the two, right? So having a good understanding about these two concepts are actually something extremely important, and you have to use them all over the places. And moving forward, we're going to talk something about a very important rule, which is the pigeonhole theorem. So some of you guys maybe heard about it, some of you guys maybe not, but it doesn't matter. We're going to talk about it. This is actually a very important concept as well. It's actually something very intuitive. But in some high-level math competition, we can use such a very intuitive rule or, let's say, a principle, try to solve some very challenging, very complicated problem. So having a good understanding for this part is very important. And then moving forward, we're going to use some lectures talking about 25 very common problems. 25 types of very common problems in counting. Like I said, counting is actually a very dynamic topic, even though you don't have a lot of formulas, right? Not like trigonometry, you have like so many identities, remember, but for counting and probability, there are only a handful of formulas. However, just using this handful of formulas, you will be able to generate so many complicated problems. So we're trying our best, try to classify them into 25 very common, very typical problems and give you guys the common strategy how to solve these 25 common problems. And then moving forward, we're going to use some lectures talking about some advanced topics in counting and the probability. So this is actually probabilities. So these are actually some complicated problems, some like more challenging problems from all over the places. So in our lecture, we always focus the problem from the North American math competition, plus some problems from European, especially like the Eastern European problems and some Asian problems, blend them together to give you guys as many exposure as possible to see different problems from different regions of the world. And at the end of the day, you might find out, okay, actually it is quite similar, even though the problems coming from different countries, but the concepts are very similar. And the strategies to solving these problems are very alike. Okay, and moving forward, we're still gonna give you something about AMC and AMY common questions. Okay, let's try to focus a little bit more on AMC and AMY, try to see how we can utilize the technology to solve some specific problems for AMC and AMY. Also, we're going to talk something about the binomial theorem. This is actually a very important theorem. And trust me, even though you might not see there's a lot of explanations for them in our day school, but as long as you go to the high level math competition, especially you go to, let's say, like the, IMO, like USAMO, CMO, so on and so forth, they try to give you a lot of hard time, in the binomial theorem related problems. So there are some common strategies, some common rules, how to solve these parts. And also, last but not least, we're going to talk a lot about the probability, okay, and this application. We're going to introduce different kinds of probabilities, the classical one, the new one, and also try to see different problems fall under into the probability category. So this is like a quick overall about what will be covered in our 10 lectures. And let me just give you a rough idea. We basically start from the very beginning, give you some basic concepts, and all the way to some flowery, complicated problems. Okay? And another different thing between our bootcamp lecture and our knowledge-based lecture, bootcamp lectures, we have many students. But in our knowledge-based lectures, the volume of our students is relatively smaller. So therefore, we have way more opportunities to have this interaction. During this lecture process, whenever you have any questions, you can always interrupt me, basically shoot your questions. You can unmute yourself, ask me a question on the fly, or you can text me. In this Zoom, I assume you guys should be familiar with Zoom, but assume you're not, you can actually go to the control panel. There's a chat icon, click that icon, you'll be able to talk to me. You can either talk to me privately, or you can make your question visible for all the students. It's up to you. So basically speaking, I want you guys to participate as much as possible. And whenever I have a questions, if you know the answers, just unmute yourself, answer my question right away, or you can privately chat with me. If I see you have the correct answer, I'm going to be asking you. Then you can basically show your answers to all the students. So this is basically where we come from in our lecture. All right, if all good, I think it's time for go to our lecture number 1. Let's go to today's concept, lecture number 1. Let's talk something about the basic concepts of counting and the probability. Okay. So talking about counting and probability, I think the most important thing is you want to count, right? That's basically where we come from. I have a complicated problem, whatever. I want to count how many answers, and what is the specific answer for such a problem. But before we go to the counting part, maybe let's try to do a quick summary for all the math problems in all mathematics. I think generally speaking, all the problems in mathematics can be classified into three major categories. The first category is you might have a complex problem. Of course, we're all dealing with complex problem. However, the complex problem actually has a very simple, or we can say very elegant solution. I'll give an example. Let's say previously we know that if I have a sequence, 1 square, 2 square, 3 square, all the way to n square, right? So this one, you have a very nice formula try to give you the answer for such a problem, right? It's a relatively difficult problem if you want to count like the perfect square sum for all the positive integers. However, we have such a nice solution. Or something like this, sine x. I don't know if you know this. Sine x could be written as something like this. Plus x5, 5 factorial, x to the power of 7, 7 factorial, all the way minus 1 to the power of n, 2n plus 1 factorial, x to the power of 2n plus 1. So this is like the famous, what we call Taylor's expansion. Okay, it means that any kind of formula, any kind of function, they can be expressed using combination of a bunch of polynomials. See, x cubed, x5, x7, so on and so forth. These are all different kinds of polynomials, right? Any kind of functions, not only sine x, you give me cosine x, ln x, whatever, all of this could be represented using a bunch of polynomials. This is what you're going to learn in your calculus Taylor's expression. But anyway, this is also a very understandable, even it looks a little bit complicated, but it's very simple, a very elegant solution. As long as you give me a number x, I would be able to use x and calculate whatever I need to calculate, right? This is a very understandable process. So this is like the first category of math problems. As long as you know that a very simple, very elegant solution, there's no need to count, right? As long as you go there, you just basically calculate whatever you need to calculate, we're good to go. Well, there's another type of problems. They're also complex. However, there's no patterned solutions. What do you mean there's no pattern solutions? It means there's no way to predict the answer. There's no way to give a formula to solve the problem. For instance, if the question asks the value about pi or the value about e, right? E is actually the base of the natural logarithm, right? So these kind of things, it is a complicated problem, right? And there's no pattern. So that being said, that there's like no way for you to solve the problem in a very short way. So this problem, you barely see that in the real math competition, right? The math competition, you barely see this problem because there's no very short, very quick solutions. You probably see that in like the talent show, like in American Got a Talent, you might remember like, I don't know, millions of digits after the decimal of pi, but you barely see that in the math competition, right? Because there's no meaning. There's like no way for you to solve it in a very quick time. Well, this is our first category, our second category. We still have a third category. There are some problems, they're still complex, and for some reason, you can find some patterns. So what do I mean by some patterns? It means that you might not have a global pattern, like one formula solves everything. However, you can basically classify, or we can use the word break out, the problem into several categories. Maybe category number 1, category number 2, up to category number K. Okay? Even though there's no global solution, global pattern for this problem, however, as long as you break out them into certain categories, let's say in category number 1, there are some pattern. Let's say number 1. And then in category number 2, you have a different pattern. We say pattern number 2. all the way category number K, we say pattern number K. So that being said, even though you do not have a global solution as elegant as you have for the first category, but at least you can break the problem into different small categories and then try to find out a pattern for different individual categories. Okay? Trust me, this problem is actually the favorite for the counting and probability. So that being said, even though you do not have a global solution, but you still try to break the problem into different small categories and try to find out a pattern for each of this category. And this process, break them into different categories and find out these different patterns for each category, we give a name. We call this enumeration. So if you Google the word enumeration, enumeration literally means what? Means list them out, right? Enumeration means list them out. But this list them out is not like a totally blindly list out everything. It's kind of finding some patterns and then list out something based on patterns. So people will say, oh, what's the difference between the two? Let's try to think about it. There are two ways to list out an answer. One way, what we call is exhaustive method. Exhaustive means you just basically try to list out everything, right? Let's say when you have 100 numbers, list out 100 numbers. You have 200, list out 200. So this is more like a brute force, right? So it's kind of very lengthy, very crappy process. So whenever you want to use this, you must make sure the set is very small, right? If you only have 20 numbers, okay, it doesn't matter. You can list them out. This is not going to hurt. But what if you have 20 million numbers? There's no way for you to exhaust it and list them out. Unless you have a computer can do it for you, right? While the other way of saying list out is actually our enumeration method. Enumeration means you want to list out the answer, but not in a very brute force way. List out everything. On the contrary, you need to find out, do we have some local patterns? Even though there's not a global pattern, we can break them into different categories and try to find out a pattern for each of this category, right? Okay, so whenever you want to break them into these different categories, of course, you need to have some criteria. Category. So what are your criteria? When you break them into, let's say, 5 different categories, you want to make sure within these 5 categories, there's no overlap, right? You don't want to do some calculation for number 1 category and then redo the same thing for number 2 category. Maybe redo the same thing for number 3 category. Of course, you're going to have a lot of like redundant answers. So when you try to do this kind of like classification, try to break them into no overlap categories. And also, no oversight. Let's say you break everything into 5 categories. You want to cover them all, right? You know what? Okay, there are still some missing scenarios. Even though this 5 categories doesn't cover them all, you won't be able to have the correct answer either. So that being said, as long as you're doing this category process, you need to have 2 criteria: no overlap and no oversight. Okay? So if you have these 2 things together, I will say you're actually doing a smart classification, right? The word smart, right? Means you want to break them into different categories, different classifications, but no overlap, no oversight, which is quite understandable, right? And the process that you enumerate them, put them into different categories, and then list out all different patterns for different categories, and then add them together eventually. This process in our math, we actually give a name because this is actually a casework. You're actually doing a casework, try to break your complicated problems into relatively understandable different categories, and then you want to make sure this casework is based on a smart classification. There's no overlap, there's no oversight. Of course, it's easy to say, but whenever you go to the real problems, there are different criteria that you need to follow in order to achieve such a nice casework. Okay? So this is basically, I think, the most important concept when we're talking about, right? These are the basic concepts we want to talk about how to start a counting and probability problem. And before we jump to all the details, all those problems, I think there are two very important concepts that you need to know in order to solve most of the counting and probability problems. Two important concepts. I think these are something quite understandable. You already know that from day one. The first one is the famous multiplication principle. So what is a multiplication principle? A multiplication principle basically means in order to finish something, let's say from A to B, you have multiple steps. Step number 1, step number 2, step number K. Okay? Try to make it easy. Let's say this is K minus 1. This is K. K is actually your B, right? Okay? In order to finish something, you have several steps. Okay? And for each of the step, you have multiple ways to achieve your goal. Let's say you have different ways to go to our step number 1, different ways, step number 2, different ways, step number 3, all the way to the last one. Let's give a name. You have N1 ways to do step number 1, N2 ways to do step number 2, and 3 all the way to NK. So the total possibility or the total combinations you can do in order to finish from A to B will be N1 times N2 and all the way times NK, right? Multiply them together. I think this is something quite understandable, right? So a quick recap is that in order to do something, you have several steps. And each step, they can't finish the work individually. Let's say you go to S1, the work is not done. You have to go to S2. You have to go to SK in order to finish everything. So therefore, the K steps, they have to collaborate together in order to make it work, right? And for each of the step, you have N1, N2, all the way to NK, different methodologies. So therefore, multiple them together, you get what you need. So this is something quite understandable. I think you guys already know that from day one, right? Just a quick recap for you guys. This is the multiplication principle. Second part, which is quite similar, that is our sum rule. Sum rule also says something similar. It means that in order to do something from A to B, you have different ways to finish the work. Different ways to finish work. And each way, they can independently finish the work. They don't need other one's help. You can independently finish the work. Let's say for way number 1, you have N1 ways. For way number 2, you have N2 ways. All the way for A number K, you have NK ways. So therefore, the total ways to solve the problem will be N1 plus N2 all to A plus NK. Is that right? It means what? It means in order to finish something, you have different ways. And each way, they can independently finish the work. You don't really have to use the help of other ways in order to finish the work. So the total ways, total, what should I say, scenarios to solve the problem is going to be adding all the ways together. A quick recap between these multiplication principle and addition principle is that can you finish the work independently? For multiplication principle, different steps, none of them can finish the work independently. They have to collaborate in order to finish the work. However, in this addition principle, or say like the sum rule, what you're going to do is any way they can finish the work independently, they just have to add all the method for each of the way, and you will be able to make it work. Does it make sense? I think this is something very, very understandable, right? You'll be able to understand it fairly quick. All right, I think that's pretty much what I want to say for our lectures one's concept. It's like so easy, right? Nothing complicated, it's like so easy. So that being said, this is actually a very basic introduction how to start your work with the counting and probabilities. So later, I'm going to give you different problems and show you guys how to do this casework, how to do this enumeration, how we can break complicated stuff into relatively easy steps, and then to make it work. All right? If all good, let's go to our first problem. Okay, let's go to our problem number one. Now, this is a fairly easy problem, but I really want to use this problem to introduce a lot of very important concepts. So this is our question number one, as shown in the diagram. Peter starts from point A to point B. He can only walk to the west, to the east, and the south. Please determine how many ways he can move from A to B. Give you the graph. Okay. So basically, you have an A point here, you have a B point here. Okay? A point and B point. And then Peter starts from the A point. They want to go to the B point. However, he can only move to the east and move to the south. It means that he can only go this way or he can only go this way. He cannot go back. He cannot go up. He cannot go to the left. It's only to the right, to the south. Okay, with all those information, try to determine how many ways that he can move from A point to B point. This is like a very easy problem, but I want to get started, try to see how we can deal with such a problem. Student got an answer 189. Not so correct. The correct answer should be 126. This is nice, right? Okay. How we can deal with such a problem? There are many ways to do such a problem. Let's try to use an easy one, a very understandable one. Okay. Well, as you can see, there's not too many. There's only like a few blocks here, right? Not too many ways. Maybe we can try to do some enumeration and list out some scenarios. Okay, so let's have a quick look at it. If Peter wanna from A to B, he only can move to the right, can only move to the south, right? So how many ways that Peter can go to this point? Who can tell me? Sophia?
One way.
Is it right? That's fairly easy because Peter can only go to the right in order to go to here. Okay. How many ways that Peter can go to this point? Enumeration just lists them out, right? There's like no way around. How many ways Peter can go to the second blue point? Who can tell me?
One way.
Exactly, right? Scarlett had the correct answer. Yes, because Peter can only just move flat, right? To the right. There's like no way around. This is the same thing as well, right? So that being said, if Peter moved to the south, move flat right, there's only one way because he can only move to the right and move to the south. There's no way for him to take a turn. That's it. Okay. Similarly, how many ways Peter can go to this point? I use the color maybe red. Just try to distinguish. Okay. How many ways Peter can go to here? You can unmute yourself if you want to answer the questions, right? So no need to really like shy or something. Yeah, you can just directly mute yourself.
One way.
One way as well, right? Yes. And same thing here. Same thing here. Same thing here, right? So that being said, as long as Peter is moving along those two shoulders, right? If I use like the word shoulder of this kind of like grid, the two shoulders are basically only one way. Okay. As long as we have this in mind, the $1 million question is, how many ways that Peter can go to this blue point?
Two ways.
Kayla? 2 ways, right? Why?
Because he can either come from the top or he can come from the left, where you add them up.
Is it right? That's a brilliant answer. Yes, because in order to go to this blue points, there are only 2 ways he can achieve. He can either go from here or go from here, right? Because he can only go to the south, he can only go to the right. So therefore, in order to achieve these blue dots, he must be arrived either from here or from here. So that being said, the total ways to go to this blue point is basically adding the number for these 2 black circles, which is 1 plus 1. It makes sense, right? If that's the case, how many ways he can come to here? Enumeration just lists them out one by one, right? But you need to find out a pattern. You're just not like blindly list out everything. How many ways if I go to this green dot? Who can tell me? Is there something very different? In order to go to the green dot, he can only go from 2 directions. One is from here. One is from here, right? Because he can only go down, he can only go right. So therefore, the total ways to go to this green one should be the sum of these 2 guys. Does it make sense to you guys? Yes or no? It's going to be 3. Okay, as long as you know this, I think the following part would be very easy. You just have to add the number of all those adjacent 2 points. Then you would be able to find out the ways to go to these points. Does it make sense? Nothing complicated. You just have to add up all the numbers together and you get what you need. All right. If that's the case, let's have a quick look at it. We already have the number for the first column. The second one, this is going to be 3, right? 3 plus 3, this is going to be 6, 10, 15, 4, 10, 20, 35, 5, 15, 35, 70, 6, 21, 56, and this is 126. So therefore, there are 126 ways for you to move from the A point all the way to the B point. You see? This is our enumeration. Enumeration means you need to find out a pattern. The pattern is basically try to add those two numbers from this adjacent 2 points, adding them together, and you get what you need. So easy, right? So therefore, 126 ways. So far, so good. I think this is a very easy problem, right? I just want to take this as an example to show you guys, okay, so this is actually, sometimes when you do not have many numbers, this enumeration process could be very straightforward. All right. This is what I call our solution number 1. It's fairly, I'll say, it's fairly easy, but you have to list out all the numbers. Actually, this problem, we can have another 2 different solutions. Solution number 2. Solution number 2, let's try to think about it. How are we going to do this? From your A point, all the way go to your B point. Who can tell me how many steps you need to write altogether? From A step, from A to B, how many steps you need to walk in total? Who can tell me? Courtney?
9.
This is something quite understandable, right? Perfect. And from this 9 steps, who can tell me how many of them are steps to the south? How many of them are steps to the east? This is also very understandable, right? Who can tell me? There are 9 steps in total, and how many of them are to the south? How many of them to the north? To the east? Kayla?
4 over to the south and then 5 over to the east.
4 to the south, 5 to the east. Right? This is very understandable. Okay. So that being said, at the end of the day, you need to basically put south, 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 south. For instance, east, 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 east. 4 south, 5 east. You can just basically do different kind of combinations for all of them, right? Okay, let's put it this way. Suppose all those 4 south and all those 5 east, they're different. I say S1, S2, S3, S4. 1, 2, 3, 4, 5. Now, how many ways in total you can walk from A to B? You're having 9 different numbers, right? In this 9 different numbers, you want to do a full permutation. 9 factorial. If you close your eyes, you think all the souths are identical, all the east, they're identical. So that being said, in total, you have like 9 factorial different ways to basically do this full permutation. But wait for a second. All the souths, they're essentially the same thing, right? And all the east, they're essentially the same thing as well. So therefore, you are overcounting a lot. Does it make sense? You're overcounting a lot. So you need to over 5 factorial times 4 factorial. Does it make sense? Because all those cells are considered to be the same, but you differentiate them whenever you use the 9 factorial. Or the 5 different yeast, they're identical things, but you differentiate them whenever you use the 9 factorial. So therefore, you need to divide them. 4 factorial times 5 factorial as the denominator. Just try to remove the kind of like the duplicate. Does it make sense to you guys? Does it make sense? Can I have some feedbacks? It makes sense, right? So this is more like from the permutations perspective, try to solve the problem, right? It's a full permutation. From a permutations perspective to solve the problem. Okay. Actually, this problem can also be solved from a combinations perspective as 3. So this is like the interesting part for our accounting, right? Same thing, but you can go for different perspectives and then you can solve the problem in different method. So my last strategy is, see, basically you have 9 steps, right? But within these 9 steps, you're going to go 4 to the south, 5 to the east. You don't really care, like 4 south, reach 4 south, the kind of different combination. You don't really care. But at the end of the day, you have 9 steps. You want to pick up 4 steps, go for the south. The remaining 5 steps will be automatically go to the east. So that being said, I think I can just directly use C94. Does it make sense? From this 9 steps, I don't really care the order. I don't really care, right? You have order, not order, I don't care. At the end of the day, you only have like 9 steps. From this 9 steps, to give me 4. They want to go to the south. The remaining 5, they want to go to the east. And then that's it. Doing such a thing. This is a combination, and you get what you need. Okay, here I want to have a quick denotation clarification. Okay, a quick denotation clarification. Because we all come from different country, we might have different naming convention, denotation convention. I like to do a quick clarification here. Whenever we do permutation, let's say from 9 numbers, you want to choose 4 doing a permutation. So there are several ways to present it. You can use A94. You can use P94. You can use 4P9. They're all talking about the same thing. It's a different kinds of ways for you to present it. So I don't know, you guys, which one you guys are more familiar with? Chris, can you give me some feedbacks from your 1, 2, 3, number 1, number 2, number 3? Can I have some quick kind of like survey to tell me which one is the one that you are familiar in your region, in your textbook, which one is more familiar? Can I have some feedbacks? Because these are all correct. Different region, like different region, different textbook, they have different kinds of like denotations. Okay, I see in our lecture, I think you are more familiar with the second one, right? Okay, so it's okay. So in my lecture, I can try to use the second one to make it more understandable for most of you guys. You know what? Actually, in most of the Asian books, they like to use the first one because P is more reserved for probability. A is actually, A is actually for permutation, but it doesn't matter. A and B and C, the 3 options, they're all correct. It doesn't matter. Okay. So another one is let's talk something about the combination. Combination, the same thing. If I want to choose from 9 numbers, I want to choose 4, try to do a combination. We also have three different ways. We can go for C94. We can go for like apprentices, 9-4, or 4C9. Again, they're all correct. Different regions, different textbook, they use different denotations. So I want to know for you guys, which one you are more familiar with. 1, 2, 3. Which one you are more familiar with? Who can tell me, please? If you want that you go to the math competition, it's okay. Whatever, they're all good. You don't really have to care about which one. The teacher will understand for everything. Okay, for this guy, I see most of the students says they're more familiar with the first one. It's okay. So just like I said, in our lecture, we are kind of focused on the ways that you're more familiar with, but sometimes I might just maybe use this way or use this way, but try to make sure we're all on the same page. These are different denotations about the same thing. Okay? So that being said, when I use C94 means from 9 different positions, I choose 4, you just let it to go for the south. I don't really care. It's the kind of like a permutation. As long as you have 4 for the south, I'm good to go. You see, these are 3 different solutions try to solve the problem, right? So using the enumeration one might not necessarily be the most straightforward one, but it's not so challenging, right? It is quite understandable. You can enumerate out all the scenarios and taking from there, solve the problem. Okay, so this is our question number 1. Okay, there are 3 ways to solve it. Now I'm going to do a very quick extension. I'm going to ask you number 2. This is actually an extension from Q1. It's exactly the same thing. I still have exactly the same. Yeah. I still have exactly the same thing. And I have a point A. I have a point B. Peter still want to go for A to B. It's all good. However, the only difference is, see here, I have a mod pole. So therefore, Peter, they cannot go for such a region. Okay, so this region has been shaded. Peter cannot go for such a region. Okay, you can only go outside, but cannot step into this region because they're like the mud pond. Okay, if that's the case, who can tell me again how many ways to go from A to B? Okay, it's not the full picture. There are certain reasons some points has been blocked. You can't go there. In that case, how can I calculate the ways from A to B? You know what? 1 minute. Think about it. And then I'm going to be asking some student to show me what you think. Think about it. Please try to post your answers into the group chat whenever you're done, okay? Yeah, I see Jerry already has the correct answer. What about the other students? All right. Okay, I see Jerry, I see Scarlett. They both have the correct answer. So I'm going to ask for Jerry. How do you solve such a problem?
Can you hear me?
Yeah, go ahead.
So we can basically divide this graph into two parts. One is on the left of the mud pond and one's on the right.
Okay.
On the left, we can see there's a 2 times 5 a pixel. I'm 2 times 5 grid and the starting point like falls on the top left corner of this grid. And we have to go to the top right, bottom right corner in order to get to B.
Yeah,
And
yeah.
for the right part, it's basically the same thing. So from A to the top left corner, there's only one way, and the end point is at the top right corner. So basically, we have to work out like the number of ways we can get from the top left to the bottom right, and then double it so that because there are two exactly same grids, so the possibility of like, I mean, the number of ways of each grid is the same, and we have to add them up. So
Okay. Yeah.
at last is 5 plus 5, and it's 10.
Okay, that's a very nice solution. Yes, nice. So I don't know, like, what about Charlotte? You have I mean, what about like Scarlett? You have the similar solution as Jerry?
Yeah, I just did like what we did in the last problem for the first one, where like for each point, I drew the number of ways to get there, and then I added the ones that were above and to the left to get the next one.
Okay, yes, actually my solution is quite similar as Scarlett's solution. Yes, I think like, but Jerry's solution is also perfect. He actually used some symmetric thing, right? And then try to calculate twice. So my solution is you can still use the enumeration because our lecture number 1 is basically focused on the enumeration, right? How can we enumerate this? We have already know that for all those shoulders, they're all 1, right? This is what we get before. And then we just continue, do whatever we did before. This part is going to be 2, 3, 4, 5. But as long as I go to this shaded area, because there's a mud pond, so that being said, there's no way for me to get to that point. Does it make sense? So that being said, the total ways to get there is going to be 0. Right? I cannot reach there means it is 0. 0, 0. So this is going to be 5 plus 0, which give you 5. Does it make sense? Same thing, 0, 0, 0. 5 plus 0, give you 5. Now you just continue to do whatever you have to do. 1, 1, 1, 6, 2, 3, 4, 10. Voila. So how many ways you go to B point? 10 ways. You see? Very understandable, right? So you still want to use the enumeration. Enumeration is you just follow the pattern. The only difference for this problem from the previous one is because you have the mud pond. Mud pond means no way to get there, means 0. And then you just keep adding all the zeros. At the end of the day, you get the total ways. You see? It's actually so easy peasy, right? This is actually an extension how to do such a problem. As long as you have such a mud pond blocking there, there's no way for you directly using the permutation or combination, right? You can use the enumeration to solve the problem. Okay? And I want to do another quick extension. Extension again. But this one is more like outside our scope. You see, this is a very, I mean, if you do not have this mud pond, you just want to have this direct one, right? You have here, you have different things. You want to go from one point to the other point, for instance. Actually, you might find out there's a pattern. Let's say here, let's say I have 4 points. So this point I give a name I, j plus 1. I, j. This is I minus 1 and j, right? You can actually find out the total ways that my I, j, the total ways to go to my I, j is always the sum of I minus 1 j plus I, j plus 1. Does it make sense? The total ways to calculate how many ways to get to my ij point, if I use function f to denote, is the sum of the total ways from I minus 1j to add ij plus 1. Right? As long as you have such an easy formula, you can actually do a quick coding using the program. You can calculate how many ways to go to whatever points. And this methodology, how to have such a thing in the programming, we call it, this is the dynamic programming. This is what we call dynamic programming. Okay, so because the value for this guy is always determined by the previous 2 guys, then you can easily, using a loop function, try to figure out what's the value for Fij. Dynamic programming is actually very important methodology. If you want to interview with like Google, Amazon, Facebook, like whatever, they will be able to ask you a lot of stuff. Yeah, you can use a loop, you can use a recursion, both things. Because most of the recursion could be converted into a loop, right? As long as we use stack. Right? Most of the way you can actually convert a recursion into a looping using a stack. Okay? All right, so this is what I want to say for our question number 1. It's fairly understandable, right? It is basically using some, some counting, some basic skills, and then you get what you need. Trust me, this kind of like going into a grade and try to solve some grade problems is very popular. So let's have a sample problem from AMC. Let's see how we're going to solve a similar problem. Okay, this is a sample problem from AMC 12. It's a problem that comes from, let me check the year. It's from the year 2010. AMC 12A, question number 18. So the problem says what? A 16-step pass is go from -4 to 4, 4. Okay, this is like a grade. Okay, and with each step increasing either the x coordinate or y coordinate by 1. Okay, so how many such paths stay outside or on the boundary of the square? -2 for x, -2 positive 2 for y. Okay, so basically, I think you need to have a graph for this, right? Okay, you have such a, okay, you have such a grid from -4 here, -4, -4. All the way you want to go to here. Here is actually 4, 4, right? And let's say, I'll give you the y-axis, x-axis. Okay. So y, this is your x, right? The question says you can't really go into -2 for x and for y. Let me try to shade it. So -2 here, right? So this region you cannot touch. You have to either go outside this region or you can touch the edge of this region, but it can't really go inside this region. All right. So let's say this is your A point, this is your B point, right? You just go from like A to B, but you can't really go inside this region. Well, who can tell me? Because now this problem is quite similar as the problem we saw before, right? How can we find out something that I can't go inside this region? Is this something similar as we just mentioned, as what we just mentioned? I think first thing first, you can't go something inside means this is like a mod pond, right? You can do a mod pond thing to put all the numbers here into 0, and then you can do the calculation exactly using the way we introduced it from here. Because you can't go inside means there's something blocked there. So solution number 1 is just basically using what? Just using the enumeration. Right? Exactly as we mentioned here. But this guy, because you have like so many numbers, maybe it takes a while if you really want to use the enumeration, list out everything. So maybe for this problem, let's try to find out some other solutions in order to make it work. Okay, Jerry?
I have an idea. So
Yeah, sure, go ahead.
basically we can calculate, like without the mod pound, we can calculate the total number of ways to get from A to B, which is C84. And then we add the mod pound and we calculate like the number of ways that goes into the mod pound. To do this, my idea is that like from A, we go to like from A, take the point like -1, -1 as example. So we from A go to -1, -1. That's C63. And then like from -1, like from -1, -1, we can get to like inside the mod pound, we can get to like that's 1, -1, and 1, 0, and 1, 1, and 0, 1, and one -1 and 1. So for these points respectively, we calculate like from these points the number of ways from these points to B, and we add them up and we time the number of steps from A to -1, -1, and then like from A we can also get to like 0, -1, and also like 1, -1. So for all of these points, we all do the same thing, and that's the total number of steps that goes
You
into
guys
the.
follow him? Yeah, I think that's a good idea. He just basically find out, I close my eyes, everything I calculate from A to B. That's a very easy combination. And then I find out the destination within all those mod points, right? And then try to subtract it from them, right? Yeah, this is actually using the exclusion. I find out the total ways and then exclude the ones that it doesn't make sense. Okay, that's a brilliant idea. My solution for this is a little bit different, but I think it also makes sense. Let's think about it. Yeah, because your goal is try to get away from the mud pond, right? As long as you calculate the way, which is get away from the mud pond, then you're good to go. Who can tell me what are the boundary conditions that I can reach into the mud pond? Let me ask you a question. If for some reason my A point reach E point at a certain stage, if I reach E point, is it possible for me to go inside the mud pond? Who can tell me? Because my point says every time they must increasing their x coordinate and y coordinate for each step. So that being said, it can always go right and go up, right? It's actually the other way around as our sample problem question number 1. This time it's always go right and go up. As long as my A point can touch E point, is it still possible for me to touch anything inside the mod point? Who can tell me? Sophia?
No.
Why?
Because anything inside the mud pond, you have to either decrease your x or decrease your y.
Is that right? That's a brilliant answer. As long as I can reach out the E point, there's no way for me to touch the mud pond. But I'll give an example. If I have a point here, as long as I reach this point, it is quite possible I'm going to touch my mud pond in the future, right? Maybe not, but most likely yes, right? If you go up, okay, you're good. But as long as you go right, you're going to be able to touch your mud pond. So E point is a very secure point. There's no way for me to touch the mud pond. What about my F point? As long as I reach my F point, is there a way for me to touch the mud pond in the future? No as well, right? Because as long as I want to touch my mud pond, my x coordinate must be decrease, but my x coordinate must be increase. So E point, and as long as I can touch E point, I can touch F point, then I'm secured. There's no way for me to touch the mud pond. It makes sense, right? Okay. If I can find some kind of like a boundaries, and then taking from there, I try to find out the boundary, the intermediate points, and then I might be able to list out all the scenarios that I'm not touching a mud point. E and F considered to be the 2 boundary scenario. As long as I touch them, there's no way for me to touch the mud pond. I think there are some other points I can do same thing. C, D, G, H. Is that right? As long as I touch C, I touch D, I touch E, F, G, H. None of them is going to make me to touch the mud pond, like the mud pond in the future. Does it make sense? So that being said, this is actually my casework. I'm trying to enumerate out all the possible intermediate point. From A to this intermediate point is going to guarantee me not ever touch the mud pond in the future. So from A, as long as I can reach C, D, E, F, G, H, it is guaranteed for me to not touch the mud pond in the future. Okay, so let's have a look at it. How we're gonna go to each of the steps. If I want to reach out the C point, in my way, if I reach C point, must be A all the way to C. And then eventually, if you want to go to the B point, must be from C all the way go to B. There's no way around, right? You can only do 1, 2, 3, 4, 5, 6, 7, 8, go to C. 1, 2, 3, 4, 5, 6, 7, 8. There's only one way for you to get from A point to B point through C point. Does it make sense to you guys? Does it make sense to you guys? It's easy, right? Okay. If that's the case, who can tell me? How many ways I can get from A to B through D point? If you can't answer this question right away, maybe let's break it into 2 steps. How many ways you can get from A to D? How many ways you can get from D to B? Who can tell me? A to D. D to B. From A to D, try to use whatever we introduced in question number 1 as the similar strategy. Luis?
8 times 8.
Can
There's
you-
eight ways to get from A to D because there's 8 transition bars, horizontal bars.
Mhm.
And there's 8 ways to get to D to B because there's like 8 paths to go up.
Does it make sense? Right? Because you can understand this something like this. From A point, go to D point. This is actually here. It's a rectangle, right? How many ways to go there? Is 1, 2, 3, 4, 5, 6, 7, 8. There are 8 ways to go from A to D. And one of them, you need to go to the right. The other 7 steps, you go up. I don't really care. From this 8 steps, you pick up 1 to go up, to go to the right. That's it. Similarly, from D point, in order to go to B point, there are 8 steps in total. You just pick up 1 step to go up, and then you're good. Does it make sense? It's very understandable, right? This is exactly what we introduced in our question number 1. Okay, if all good, who can tell me how many ways to go to E point? And then, furthermore, how many ways from E to go to B? It's quite similar, right? You know case number 1, case number 2, case number 3 is exactly the same thing. From A point, you want to go to E point. How many steps in total? And how many ways you need to do what? Very easy. Who can tell me? Who can tell me? I'll be asked. Is this something very challenging? How many ways from A to E? I'll be asking for Kayla.
Since we have to go 6 north or 6 up and then 2 to the right, it's 8, choose 6, or you choose 2.
Is it right? Exactly the same thing. In order to go from A to E, you have 8 steps. From these 8 steps, you just have 2 steps going to the right. The other way you go up, I don't really care. So this is going to be C8, 2. From A to E. Same thing from E to B. Again, C8, 2. Very understandable, right? Okay. As long as you know the ways to go to C point, go to D point, go to E point, what about the remaining 3? Do you have to calculate it one more time? Or it is very conspicuous? because check out the position CDE, FGH. They're kind of symmetric, right? So the numbers of ways to go to F point will be the same as your E point. The number of ways to go to G point will be the same as D, and H will be the same as C. So that being said, your F is going to be C8, C8. Your G, C8, C8. Your H will be 1, using the symmetric property. Right? These 3 points are actually symmetric versus these 3 points. So therefore, adding them together, you get what you need. So now you break the problem into 6 different cases. You need to add them together, right? Add all those numbers together. The answer will be 1698. See? Fairly understandable. Using our casework, break them into different cases and make sure your smart classification, there's no overlap, there's no oversight, so you are good to go. So far, so good? I think this is something quite understandable, right? It's a very understandable process. So Louis got a question. Why is 8 choose 2? It's not 7 choose 2. Yeah, because there are 8 steps taking from A to E. I'll walk you through. 1, 2, 3, 4, 5, 6, 7, 8. There are 8 steps to go from A to E in total. You need to choose 2 of them to go for the west, to go for the east. Okay? So, yeah, that's a very simple mistake. Do not make any simple mistakes. Okay? So this is actually a very typical problem. You're going to see that from time to time, right? Try to play with different grades and solve the problem. Having the casework is always important. You need to know how to break them into different cases. The most important thing how to break them is try to analyze the problem, and taking from there, you might be able to have an answer. Okay, if all good, let's move forward to another question. So next question, let's go for, again, question, this 2-part. Let's go for also the AMC12 problem. This is a relatively difficult AMC12 problem. It's 2017 AMC12B, question number 22. Still a casework. Let's try to understand how to break them into different cases, how to analyze the problem, and taking from there, break them into different cases. So this problem says I have Amy, Bernardo, Carl, and Deborah. They play a game, A, B, C, D, 4 people. They play a game. In which each of them starts with 4 coins. Okay, you have 4 coins. The game consists of 4 rounds. For each round, 4 balls are placed in the arm. 1 green, 1 red, 2 whites. Okay, 3 different colors. The players each draw a ball at random without replacement. Whoever gets the green ball, give 1 coin to whoever gets the red ball. Okay, so you see, you have 3 colors, 1 red, 1 green, 2 whites. So the people who get 2 whites, they don't really do anything, but the green and red, they basically do a coin pass up. Now, what is the probability that at the end of the 4th round, each of the player has 4 coins? It means at the very beginning, everyone has 4 coins, and after OER blah, 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 nothing has changed. Still, everyone has 4 coins. How are you going to deal with such a problem? You see, we have like 4 people, A, B, C, D. Basically, the coins are actually passed on between these 4 people, right? At the very beginning, you have 4, like everyone has 4 coins. And then after your 4 rounds, everyone still have 4 coins. So think about it. Every time there will be 2 people, 1 people give another people, 1 person give another person a coin, right? Every time this is going to happen. So after 4 rounds, The coins are exactly the same. Who can tell me how many people could possibly get involved into this game, this exchange game? We have 4 people, A, B, C, D, right? 2 of them could be white, they don't really participate, but 2 of them could participate. So how many people it is possible that get involved in this game to make sure at the end of the day, they still have the same coins? So let me ask you a question. Is it possible only 2 people get involved? Yes or no? Is it possible only 2 people get involved in this 4 rounds? Who can tell me? Is it possible only 2 people get involved in this 4 round? Only 2 people. Luis?
They each give 2 to the other person, so I think it's possible.
Is that right? It is possible. Only maybe me and Luis would, like, first time I lose, second time he lose, and third time I win. And then, just basically just like a C and D that doesn't really get involved. There's only 2 people that get involved. It is quite possible. Is it possible 3 people get involved? Three people get involved. Is it possible? Three people exchange their coins, but after 4 rounds, they are all good. Think about it. We try to do the casework based on different people. How many people get involved into this game? Actually, it is possible. Why? You might have A, B, C. A and B exchange for one time. C and D, B and C exchange for another time. You only have 4 times. A and B, 2 times. B and C, 2 times. Right? It is possible that only 3 people get you. Is it possible 4 people all get involved? Who can tell me? Is it possible 4 people all get involved? Please participate in the discussion. I like to hear what you think. 4 people all get involved. And then at the end of the day, everyone has the same coins. Who can tell me? Kayla?
If there's 4 people involved, and the coin goes to each person and then goes back to the first like A to B to C to D and back to A.
That's perfect. One way, right? Having a big circle. You just take a circle, you have it. Is there some other possible patterns for this? One way is like 4 people have a big circle. That's it. Is there another pattern that also get 4 people get involved, but something similar? Luis?
Well, you pair A, B, and C, D together, and they each give each other ones.
Does it make sense? Right? Only A, B play together. Only C, D play together. But they don't have this interchange for everything. I think you only have like 4 people. And at least 2 people need to get involved, right? 2, 3, 4. You cover all the scenarios. So this is case number 1, case number 2, case number 3. Let's try to calculate the numbers for each of the case. First thing first. 2 people get involved. 2 people get involved. How to calculate the total scenarios? That one is easy. From 4 people, I choose 2. I don't know, A, B, or C, D, like whatever, right? 4 people choose 2. And these 2 people, okay, 1 lose 2, 1 win 2, right? If you use lose and win, right? Lose means you give a ball to the other, win means you have a ball. In total, you have like 4 rounds. 2 rounds go to 1 people, and then automatically the other 2 rounds go to the other 2 people. So therefore, 3 for 2. You don't really care the order, right? Because as long as you win 1, then automatically the other one lose 1. You don't really care about the order. As long as just 4 games, you win 2, he lose 2, that's it. That one is easy. 36. Let's go to the second one. A, B, C. 3 people get involved. 3 people get involved. So first of all, from this 4 people, reach 3 get involved. Is it A, B, C, A, C, D, B, C, D, right? And then from this 3 people, there must be 1 in the middle, right? There must be 1 actually doing the kind of like the liaison, like the hub in the middle. Reach 1 from the 3 in the middle. Now, it actually, the remaining part will be 4 games, right? A win B, B win A, B win C, C win B. 4 games. Reach 1 happens first. Reach 1 happens later. So you don't really care. You can do a full permutation, right? A, B, B, C. Reach 1 wins, reach 1 lose. You can do different combinations. So basically 4 different games, 4 wins, 4 lose. You do whatever you want. Now it's going to give you 12 times 24. It's very understandable, right? The process is very understandable. Now, 4 people get involved. If 4 people get involved, let's have a look at it. How are we going to deal with that? If this is like a big circle thing, if this is like a big circle thing. So A, B, C, D, you want to have a big circle. The first player comes in. I don't know if it's A, B, C, D, or like whoever, right? First person, let's say A, he can win 3 people. He can win B, he can win C, he can win D. He has 3 options. As long as he chooses B, for instance, when B comes in, B only has 2 components. B opponents. B only has 2 opponents. One is C, one is D. He can win C, he can win D. He only has 2 options. Right? As long as he chooses for C, D has no way around, right? C must win D and D must go back to A. So these are 1 times 1. Right? And this is actually who wins who. But in terms of A wins B in the first round, or B wins C in the second round, C wins D in the third round, D wins in the fourth round, or some other permutations, yeah, this can be P44. Who wins who in the first round, who loses who in the second round, I don't really care. You do whatever you like. So this is basically a full circle permutation thing. It makes sense, right? All right. Let's go for the last one. A, B, C, D. Again, let's say I find an A. As long as I choose A, I have B, C, D. 3 guys. I can choose 1 as my opponent. I have 3 options. But as long as B has been chosen as my opponent, C and D automatically, they will be a group, right? There's no way around. So C and D, they automatically, everyone just have one option. Does it make sense? Right? As long as C and D, they're all chosen, A wins B, A lose B. C wins D, C lose D. I don't really care. You do whatever you like. So in total, you have P44 different combinations. P44 different, I'll say permutations, right? I don't really care who wins first, who loses first. It doesn't matter. So therefore, you can see there are 3 different ways to make your classification, 3 different cases, and these are the total number of my 3 cases. You have to add them together, right? So if the question asks you to determine the probability, so we're going to talk about probability later, but here we can definitely do a quick talk. Probability means the desired scenarios over the total scenarios. Desired scenarios over the total scenarios. Desired total scenarios is your 1, 2, 3, 4, adding them together. And a total scenario. So what is the total scenario? Total scenario is it's like 4 people, they play random game. Every time there's a winner, there's a loser, right? Every time there's a winner, there's a loser. The 2 like 2 ties, I don't really care, right? 2 whites, I don't really care, right? So when you choose the winner, you have 4 options to choose the winner. As long as you choose the winner, you have 3 options to choose a loser. The other 2, I don't really care. This is for 1 game. And there are 4 games in total. Every time you can have 4 as a winner, 3 as a loser. So this is going to give you the total answer for such a problem. This is not an easy problem, I have to say, even though it's an AMC 12, but I think the complexity goes to the mid, or like it's a relatively mid-level AME problem, because every single step you need to make it correct in order to make the overall thing work. Does it make sense to you guys? You see, this is a very interesting problem that you can do the casework. Using the enumeration and the casework, this time you're actually using the people who win the game, or who get involved in the game. Could be one, could be 1 pair, 2 people, could be 3 people, could be 4 people, all get involved into the game. So far, so good. So this problem is not so easy, right? Okay, if all good, let's advance. Okay, our problem is getting more and more complicated. Now, let's go for an AME problem. We're all using the same strategy, right? Nothing has changed. We're all using the same strategy. And then let's do the problem gradually by gradually, more and more difficult. Now, let's go for 2007, AME 1, question number 10 problem. This is also a very typical problem. I like to show you guys the thinking process for such a type of problem. So the problem says you have 6 times 4 grid, 6 rows, 4 columns. 12 of the 24 squares, of course, you have like 24 squares, right? 12 of the 24 squares are to be shaded, such that there are 2 shaded squares in each row and 3 shaded squares in each column. Okay, you make this arrangement is every row you have 2, every column you have 3. Let n be the number of the shadings with this property. Find the remainder when n is divided by 1000. So basically, because Amy is actually a number from 0 to 99, so therefore they want to do a remainder to make sure the number falls into that range. So this problem goes like, try to insert the graph. Having a nice graph is always very important as long as dealing with something relatively complicated. Let's have a quick look. So this problem says what? You have such a grid. You have 6 rows, 4 different columns, right? And in this 24 cubics, you want to have 12 of them shaded, such that each row, each column, you have different scenarios, so on and so forth. Well, this problem is that, you have like so many, you have like 12 different grids, right? They have 12 like different cubics. So how can you do the casework? Are you going to get started with like 12, all of them? That's going to be crazy, right? You don't know how you're going to do the casework. As long as you see such a problem, a certain number of cubics should be colored into a certain color, so on and so forth. You know what? Never be panicked. Your casework must be start from different rows or different columns. This is very important. When you do the casework, must be start from different rows or start from different columns. Okay? Because you can't just randomly 12 cubics. It's not so easy for you to do the casework. But which one you want to start with? I suggest to start with whichever is smaller in numbers, or we can say in scenarios. Because you have 6 rows, you have only 4 columns, and I suggest you to stick on the columns because you only have like 4, right? You don't have to go for too many different cases. Okay, now step number 1, you understand. I must start from columns. All my casework must be focused on the columns. Second step. Even for columns, it's not easy, right? You have 4 columns, and each column, they have 3 squares shaded. So these 3 squares can be randomly patterned all over the places. Don't be panicked. Always start with only 1 column shaded. Okay, so this problem, you have 4 columns. Always start with only 1 column. Okay, these are like the rules how to do such problem. But for this, let's start with the first column. The first column, the question says 3 squares must be shaded. So these 3 squares have like so many options, right? You have 6 cubics, and you want to go for 3. You have like 3 different options. No worries. Step number 3. Always move the cubics or the squares to the very beginning. You can have this, right? You can have this. But it's too complicated. No worries. Always move everything to the very beginning. AKA, let's go for a very easy scenario. Go for here. People will say, hey, Alex, it is not guaranteed that all the 3 blocks are at the very beginning, right? It doesn't matter because randomly from the first column, if you want to pick up 3, you have C6, 3, right? Which is 20 different scenarios. Without a loss of generality, we let the 3 squares goes to the top. Okay? So later, whatever you calculate, eventually you times 20. That's going to cover everything. Okay? So now your first column has been fixed. Let's go to the second column. Well, if you go for the second column, again, you're facing, right? You're always like, you can put like the second column, you can put wherever you like to put, right? This guys can be randomly put. So this is our rule number 4. When do the second column, always start with the same pattern as the first. Okay? Whenever you start a second column, do not randomly do anything. Try to start with the same one as you did for the first column. Because in that way, your life can be easier. Everything could be linear, could be similar. If you just randomly put everything, this is going to be a nightmare. So let's say my second column, I go for here. Okay. If my second column goes for here, who can tell me how can I arrange my third and fourth column? How many ways I can arrange my third and fourth column? Who can tell me? You have to make sure every column you have 3. Every row has 2. You have 2. So if the second column is arranged like this, what about the third one and the fourth one? How many ways you can allocate for the third and the fourth column? Who can tell me? Think about it. Like the way I ask you like this, it won't be too complicated, right? If you have like 1,000 ways, I won't ask you like this. So how many ways you can arrange for the third one and the fourth one? Respecting whatever the question asks you. Each column has what? Each row you has what? Kayla?
There's only one way because in columns 1 and 2, there's already 2 in each.
Is that right?
In the other columns, they have to be enough remaining 3 rows.
Exactly. As long as you have such a constraint, trust me, there's only one way for you to arrange the third and the fourth column. Right? Because the first 3, you cannot put anything. The first 3 rows, you cannot put anything. The first 2 columns, you cannot put anything. Everything must happen in the last 2 columns, the last 3 rows. That's it. And you have to pick one for each. So that being said, if I could case number 1, this is my case number 1, right? If my second column is exactly the same as my first column, there's only one option for me to make all those arrangements. Okay, understandable. Then what about my second column is not exactly the same as my first column? Okay, my first column is always like this, right? Now let's focus on the second column. In my first case, case number 1, my case number 1 is what? My second column is exactly the same as my first column. Well, my second case is that my second column is not always the same as the first column. It means what? The second column will have two squares superpositioning with the first column, while the other square is not superpositioning. Okay? My second column has two positions. Change the color. Superpositioning with your first column, but the other one is not superpositioning. Which makes sense, right? At the very beginning, they're exactly the same. Now I only overlap two. Okay? In that case, let's try to think about it, how we can arrange that. This is my case number 2. Well, in order to make sure my second column only have two superpositioning with your first column, and the other one is not there, how many ways I can do this first two requirements? Only two superpositioning and another one not superposition. I'll be asking for Luis.
3 choose 2 times 3.
Does it make sense? Only two superpositioning from 3 choose 2. And the other one is not superpositioning. You only have 6 rows in total, means for the remaining 3, you choose 1. Okay. As long as you have this, you're still gonna go for the column 3 and column 4, right? Who can tell me how many ways you can range? In my picture, right? This is one example, right? How many ways you can arrange the third and the fourth column? Who can tell me? How many ways you can arrange the third and the fourth column? Think about it. Get your hands dirty. This is the enumeration part, right? You have to really try some casework. How many ways you can arrange the fourth, the third, and the fourth column? Think about it and try to post our answers into group chat. Again, it won't be too many, right? Like the way I ask you, it won't be too many. Okay, I see two students. They both say have 4 ways. Maybe let me show you my ways, and then maybe you can tell me which are extra. Okay? So first thing first, the first 2 rows, this row is correct. This row is correct. So this row is a missing, right? You missing one, just like one shaded square. So this one could be here, or could be here, right? You only have 2 positions. Could be here, could be here. Okay, so let's go for this way. If this goes to here, let's go for the first one, and then it's going to be here. Here, 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 here. Is it right? You want to make sure each row has 2, each column has 3. Or as long as it goes to here, it's going to be here, 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 here. Is that right? I think there are only 2 scenarios. I don't know why, like, you think there are 4 scenarios. Is there anything that I missed? Am
Wait,
I
I have a
missing?
question.
Sure, go ahead.
If you think about it the other way, where you choose the 3rd column first, and then the remaining 3 would be the 4th column. Or actually, wait, if you just do it this way, why can't the 2 x's be on the same row?
X must be 2x on the same row, yes.
Yeah, so why can't you have like well, for the first one, instead of the gap at the 2nd spot, why can't you have it at the last spot?
That's exactly my second scenario. My second scenario and my first scenario, they're exactly, I swap row number 2, 3, and row number 4. This guy, I'm going to see. This guy and this guy, the only difference is this is number 3, this is number 4, right? And now number 3 goes to here, number 4 goes to here. So I just swap the 2 rows to number 3, number 4. Can you tell me, what do you think?
Oh, wait, I think I overcounted because I instead of the gap, because you have the gap at the 3rd row, the 4th row, I put it on the 5th row and 6th row as well, and then
but that's going to be the same thing, right? But that's going to be the same thing. Because
no, wait, if you put a gap at 5th row and 6th row, that doesn't leave a spot for the that only leaves 2 spots.
You have to make
So,
sure every
yeah.
single row there are 2, every single column there are 3, right? Because this guy, what I'm trying to say is, this guy, these 2 rows and these 2 rows, I mean these 2 columns, they're exactly the same thing. I just swap. One is number 3, one is number 4. The other one is number 4, one's number 3. But the patterns are exactly the same. Does it make sense? Right? So
Yeah.
that being said, perfect. So that being said, even though it looks like so complicated, when arranging the 3rd and the 4th column, there are only 2 scenarios. Right? In my specific graph, there are 2 scenarios. And my specific graph is actually one representative of all my C32, C31 different combinations. So in total, it's going to be this guy times this guy times this guy. That one is going to give you 18 different scenarios. See? We always go for such a pattern. We start from the first row, the second row exactly the same as first row. A little bit different with the first row. Gradually, we'll be able to cover everything. With all of this, who can tell me what is my case number 3? What should be my case number 3? My first scenario is case number 1. Second row is exactly superpositioning with my first row. My second case is my second row only have 2 positions superpositioning with my first row, while 1 position not superpositioning. Then intuitively, what's going to be my third case? Luis?
You have 1 superposition.
Is it right? It's very intuitive. So this classification process is very understandable. You have no 3 superpositioning, 2 superpositioning, 1 superpositioning. The last one is going to be no superposition. You already forecast what's going to be the cases. So these cases are not like random. Okay, let's go for this. Let's go for that. There's a rationale behind it. You're just doing this gradually by gradually by gradually. Every single step is going to be very understandable. So let's go to case number 3. Go for here. Case number 3 will be only 1 superpositioning. Only 1 superposition. And that means what? My first is going to be here. My second, here, there's only 1 superposition. I'm going to give an example maybe here. Oops. And then 2 of them not superpositioning. So only 1 superpositioning. And 2 not. 2 not superposition. Okay, let's go for the first one. Only 1 superposition. How many ways? In order to finish the work, you have 3 steps. Step 1, only 1 superposition. How many scenarios? Step 2, 2 not superposition. How many steps? Step 3, what about the remaining third row and the fourth row? Third column, fourth column. Only 1 superposition. C31, right? From this 3 black shaded position, reach 1 is actually superposition, C31. And then 2 not superposition, C3, C3, 4, C32, right? C32. Yes. Now, the most important thing is how can we do the remaining part? Third column, fourth column. This is something a little bit challenge. You have to think about it. Think about it. In this scenario, how can I deal with the third and the fourth column? This is the most challenging part. But again, don't be panic. We have to do some analysis. So your goal is try to do 3 and 4, right? You won't be able to do them all together. Maybe let's do this one by one. First, you need to do number 3, and then you go to number 4, right? Let's go for the third column. For the third column, let's try to use the color blue, or maybe yellow. Just try to make it a little bit different. Okay. You have 3 blocks to put, right? 3 blocks to put a color. Can you do the first one? Can I answer? Who can answer my question? You have three like little cross, right? To put it into the third column. Obviously, you cannot do the first one. I'll use the color maybe yellow. It's actually easier. Because the first row already has 2 cross, right? There you can't really put anything into the first row. And what about the last row? You must put something in the last row because the last row has no cross. You need to put one, and then later, like the 4th column must come here and do the last one as well. So that being said, you have 4. 1, 2, 3, 4. You have 4 remaining empty seats, and you need to put 2. And you need to put 2 cross for them. Is that right? First row you can't take because there are already 2 crosses. Last row you must take because there's no cross. Remaining 4 positions you have 2 cross to put. So C4 2. Does it make sense? Okay. As long as you put anyone, I'll give an example. Let's say you put here. As long as you put it here, you know what? For the last one, sorry, you need to put 2, right? You put 2. As long as you put a third one, right? How many scenarios you can go for the last one? There's only one scenario you can go for the 4th column. So therefore, times 1. Does it make sense? I'll have to quick recap. Now, the first column is already done. The second column, there's only 1 superposition, not 2, not superposition, okay? You just give a random guy, right? Like the one I show in my graph in color red. So now let's go for the third one. Let's go for the 4th one. The third one, you know, the first row, you cannot put anything because already a black, already a red. The last one, the last row, you must take 1 because there's nothing there. You must put a yellow. So that being said, there are 4 positions remaining. Maybe I'll use the blue. There are 4 positions remaining. You need to put 3 crosses for each column. So therefore, you can randomly put 2. As long as you put 2 there, you see, the 4th one, there's only 1 position. There's only 1 scenario that you can do. Okay? If you don't agree with me, no problem. Let's go for another one. If I go for, I don't know, go for this guy, for instance, then your last one is going to be this one, this one. Still only 1 scenario. So that being said, as long as the third column has been defined, the last one, there's only 1 option. So this is actually our case number 3. You multiple all of them together, that's going to give you 54. Does it make sense to you guys? Does it make sense to you guys? Can I have some feedbacks? It makes sense, right? Every single step, there's a reasoning, right? Okay. We have O superpositioning, 2 superpositioning, 1 superpositioning. Intuitively, the last case would be my first row and the second row as a 0 superpositioning. See, it's very understandable. Case number 4. no superpositioning. There's a rationale, right? Every single step, there's a reason. Okay, means no superposition means my first one, 1, 2, 3. My second one, no superpositioning. No superpositioning has no other route, right? No way around. There's only one option. Okay, and your goal is do the third row, do the fourth row. I think for now, if you want to do the third row, you do whatever you want to do, right? No one is going to be in your way, right? So think about it. What you can do for the third row and the fourth row. Give you 1 minute. Think about it. Again, you want to go for number third row, number fourth row. Sometimes don't be too greedy. You can't have all of them at one shot. You can just gradually by gradually do one row, do the other row, and then so on and so forth. For my third row, I'll be asking for Kayla.
Since in each of the rows, none of them have 2, so any the squares can be shaded. So you have 6 options, and you have to choose 3. So you pick choose 3.
Is it right? Because like everyone has a cross already, so you just do whatever you like, right? Okay, as long as as long as you choose anyone, 1, 2, 3, I don't care. Then how many options you have for your last row? How many options you have for your last row? Luis?
Only one.
Right? Exactly, because for now, for my such arrangement, you can put only here, here, here. If you don't agree with me, you want to change for different arrangement, I'm gonna go for here maybe. I'm gonna erase it. If you don't think this is right, I'm gonna erase it. If you put a third one into here, 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 then unfortunately the last one can only go for here, here, here. So as long as the third one has been chosen, the fourth one, there's only one way. So how many ways you have? Just C6, 3, which is 20. Okay, so that being said, you have 4 cases, right? These 4 cases, I always go for, we have introduced different ways how to do this. I always go for the first one, put everything into the 1, 2, 3, the very top, and then basically do the overlapping, all overlapping, part of overlapping, all the way to no overlapping. So how many cases you have? Case number 1, you have 18. Number 2, you have 54. Okay, excuse me. Number 1, you have 1, right? Number 1, you have 1, right? Number 1, case number 1, you have 1. Number 2, you have 18. Number 3, you have 54. Number 5, you have 20. So it's going to be 1 plus 18 plus 54 plus 20 equals to 93. 93 scenarios based on what? Based on the assumption that you put all those 3 dots, 3 cross at the very top, right? 3 dots at the very top, very top. These are actually based on the first scenario. But like I said, there's no guarantee you're always on the first top. You have C6, 3 different ways, to choose your first, to choose the 3 cross for the first column, right? Say 3, even 20 ways. So therefore, in total, it's going to be 3093 times 20, 1860. These are the total ways to make such an arrangement, right? So the question asks, what's the remainder when this guy modulo 1000? Of course, it's going to be 860. That's the answer for such a problem. Okay? Again, try to use this problem, follow the way how we do the casework. As long as you have this very complicated number of things, you have different rows flying there, first, try to start with whichever is actually easier. You start with rows, it's still good, but you're going to go for more cases. Start with columns, it's actually easier. Second is, always start with the first row, if you choose row or if you choose column. Start with the first. But while the first one, they can be choosing like different ways, always push them into the very top. That's really going to help you to simplify the problem. And then moving forward to the second row, third row, fourth row, based on the superpositioning. All superpositioning, only one superposition, 2 superpositioning, 1 superpositioning, all the way to no superposition. This is actually the way how you blend them together. Okay, you see, with my analysis, this problem is very understandable, right? Not something too complicated. All right, so this is what I want to say for our lecture number 1. Lecture number 1 is not a very, what should I say, very complicated, very high-tech thing. We just go for some basic concepts in the counting probability. AKA, we focus on the, the casework, the enumeration, try to break them into different scenarios and try to find out a pattern for each of the scenario. And then try to remember when you're going to use the multiplication, when you're going to use the sum, right? Depends on different ways or different steps. So these are all considered to be the overall concepts, right? We never go into something too complicated or too specific technologies, are basically based on the overall understanding, do some counting, count the numbers, and then add them together. This is like the very beginning of our lecture. From the next lecture, we're going to go even deeper into the permutation and the combination. We're going to teach you guys different ways when you're going to use the permutation, when you're going to use the combination, especially when you have a circle, what are you going to do? Especially when you have a group, what are you going to do? So these are considered to be more specific topics for the permutation and the combination. But for that today, it's more like a generic way how to break them into different cases, how to calculate different cases, how to add them together, and this is the general way how to do our thinking process. All right, that's actually the lecture number 1 of our counting and probability. You have any questions for me? Are we all good? So try to bear in mind that I'm always be reachable offline from WeChat or from like Google Class. If you have any questions, you can always let me know. All right. In that case, that wraps up our today's lecture. And later, I'm going to upload our assignment to the Google Classroom. You have 1 week to finish your assignment. And in the next week, I'm going to be asking some students who did it correct in assignment to give us a quick walkthrough. How do you think for all your assignment? All right, that's pretty much for today's lecture. If all good, I wish you guys a good weekend. I'll see you guys for the next week. Okay, bye guys. Have a good one.